Welcome everyone to day 4. If you could be taking your homework out first. Second, you can be writing in your planners that you've got your day 4 homework worksheet. That's right in your packet. So the next page after where the previous class's homework was. And then once you have done those two things, you can be checking your homework answers. Try to resolve them first with people sitting nearby you to see if they can point out any mistakes in your work. And we're going to pause the video for 2 minutes for you to check each of those answers. All right, so I'm going to scroll through the written out answers. There's not a whole lot of work for most of these ones, but if I'm going to pause on the screen on the slide for about 10 seconds or so. If there are any of the ones on that screen that you wanted to take a longer look at, just shout out to the sub, say pause please, and they'll pause the video for you to check and see where you went wrong, and then let them know when they can hit play again. So again, we're gonna leave it here for about 10 seconds. Just shout out to the sub, say pause please if you need it to stay on this page, because it'll only stay here for about 10 seconds. And the rest of them, again, we'll leave it here for about 10 seconds. Say pause please if you need the sub to leave it on this screen so you can check your work. And then let them know when they can hit play again. Okay, so we're going to be in our notes packets where it says BC 2-4. And what we've got here is we've got a graph. If we check our axes, the x-axis is hours, the y-axis is miles per hour. So this is a velocity graph that we are looking at. And it's representing the velocity of the car over a 5-hour period. So what we're going to do is we're going to pause the video for 2 minutes, we'll say, and with some folks nearby, see if you can talk about how far did the car travel and be able to tell the people nearby how you figured out how far the car traveled. So again, we'll pause it for 2 minutes for you to do that with some folks that are nearby you. All right, so we should have gotten 190 miles is how the car traveled. A couple of ways we could have done that. Because each section has a constant rate, we could have used the formula distance equals rate times time. So for the first section, your distance would be your rate of 30 miles per hour times 3 hours. So we would have went 90 miles for that first one. The second one, our rate was 50 miles per hour times the 2 hours that it traveled. So that was 100 miles. And then just put them together to get the 190 miles traveled. Now note, so we did 30 times 3 and 50 times 2. Notice those calculations are the same as if we just did the area of each of these rectangles. That's a 3 by 30 rectangle and a 2 by 50 rectangle. And then we just added up the area that's underneath our velocity graph. So if you have a velocity graph that's representing some scenario of an object moving, and you want to find how far did it travel, well, you can just take the area of the space that is between that velocity graph and the x-axis. So in this case, we just had to do some areas of rectangles. So that's great. That's a very powerful thing. But If we go to our down below, what happens though when the velocity graph looks like one of these? Underneath those velocity graphs are not shapes that we have a nice area formula for geometrically. So that becomes a problem. So we're going to start out by investigating that x squared plus 1 area that's on the right there. So if we go over to the next page, we're going to use a technique called Riemann sums that will help us find the area under a curve. Now, when you hear me use the terminology area under a curve, really what that means is the area between the graph and the x-axis. So what we're going to do here is we are going to split this into 10 vertical strips. Well, in case it's hard for you to see here, this point is 2, 0. So that's x equals 2, and we're starting at 0. So if we're going from 0 to 2, and we want to split it into 10 vertical strips, we've got to figure out how wide each subinterval should be. Well, we're essentially going to do 2 minus 0 and divide it by 10. So that will give us 0.2. And the general technique is we did where the interval ends minus where the interval started and divided it by the number of subintervals that we wanted. So our strips, each of these dots is going by 0.1. So we'll go every 2 tick marks, and that'll give us our strips that we're going to work with. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, looks like we got our 10. Okay, that's broken down the problem a little bit. If we can find the area of each of those strips and then just add them together, that'll give us our area that's underneath the curve. But still, each of those strips is not a nice shape that we have an area formula for. It's got a base. It's got some vertical edges that are not consistent, but then it's got a curve on that top edge. So how do we go about doing that? Well, what we do is we're just going to do an approximation. And the way to approximate it is to do a figure whose area is really easy to calculate. And as we saw on the first slide, something that's really easy to calculate is the area of a rectangle. Now the rectangle, we'll have to make a decision of how to figure out where that height of it should be, because we want it to be flat. And there's 3 main different ways we're going to do this. So if we go to the next slide, it's the same picture. It's got our slices already divided up. And we're going to do this with the right endpoint method, which is also referred to as an upper sum. The reason it's referred to as an upper sum is because the right endpoint is the higher x value in the interval. So like in that first interval, the x value starts as 0 and ends as 0.2. Well, the upper edge of that would be the 0.2, or in other words, the right endpoint. So I'm going to draw my first rectangle actually in the last interval because it'll be easiest to see. So in this interval here, I'm going to go on the right edge of it until the right edge hits the top. And what you're going to do is just draw a horizontal line straight over and then down. And that's the rectangle we're going to find the area of that will be our approximation for that strip. Well, then the next one will look like this, because we're going to go on the right edge of that interval to where it hits the graph and then go over. And then we'll keep doing that for each of them. So notice the height of each rectangle is dictated by how high the right hand edge y value is. So the rightmost x value in the strip, whatever its y value is, that is the height we will use for the rectangle. Well, each rectangle is a base times a height. One thing that's convenient is all the bases are 0.2. So we're going to do 0.2 times one height, then 0.2 times another height, then plus 0.2 times a third height, and so on. Because the 0.2 is going to be in all of them, we're going to just factor that out. So we're going to put 0.2 out front. And then the height of our first rectangle over on the left there is the y value when x is 0.2. So we're just going to have f of 0.2, and that's going to represent the first height. So the second rectangle, when we go left to right, we will be using the height when x is 0.4. So we're going to have f of 0.4 for that next one. And we're going to keep going. We'll have f of 0.6 plus f of 0.8 plus f of 1, f of 1.2, and we're going to keep going by 0.2s all the way till we get to 2. And if you count it up, how many f ofs we have there, there should be 10, and that represents our 10 strips that we have. Now, by f of 0.2, what that's saying is we're subbing 0.2 into the x squared plus 1, and that's giving us the y value that is then the height of our rectangle. And again, essentially that 0.2 out in front of the parentheses is distributing to each of them, but that base of the rectangles were consistent for all of them. So let's show you how we can put this in our calculator. So rather than actually subbing 0.2 into all of them, let's add a graph page. So we'll give you a moment to get your calculators out and then go to a graph page. And in the graphs page, we're going to put in the x squared plus 1. And hit enter. Now note mine is in F1. If yours is in something other than F1, you will want to note that for what we're going to do next. So next we'll go to a calculator page. I already had one open, but if you didn't have one, you can do Control and then Doc, which is below on, to add a calculator page. And we're essentially going to put this in the calculator, and I'll show you where you can get the function notation where it'll automatically sub into our function that we want. So we're going to have 0.2 parenthesis, and then above the 9 is the button VAR for variable. If you click that, notice F1 pops up. That's the only function that I have defined. So I select that, and notice it's bold. That means it recognizes that as a function from our graphs page. Then I'll just put in 0.2 and close the parenthesis. And what that's going to do eventually is that I'll put 0.2 into our x squared plus 1 automatically, and I don't have to worry about subbing it in with parentheses and everything like that. So now I'm going to do plus, I'll do variable again, and I'll do 0.4 and close the parenthesis. Plus variable f1, 0.6, and so on. And I'm going to do this all the way up until we get to 2. So we'll give you some time to do that on your end as well. Now it's really easy to forget a parenthesis or a plus sign. So after we type it all in, before we hit enter, you're going to want to just scan through and double check to make sure you did not miss something somewhere. Okay, so I got all mine typed. I'm just going to scroll through, make sure I've closed the parenthesis. I've got all my pluses in there. It looks like mine's good. So I'm going to go ahead and hit enter, and I get 5.08. Now, the notation to represent this sometimes is you'll see a capital letter with a subscript of how many rectangles you did. So we would sometimes call this R10. And this R10 just represents our Riemann sum. Okay, this technique we just did here where you split an interval into a bunch of rectangles and add up the rectangles as an approximation of the area under the graph, that is called a Riemann sum. The capital R is representing that we used right-hand endpoints as our reference for the heights, and the subscript of 10 just means we split it into 10 strips. So that 5.8, it should be a pretty decent approximation of that area that is under the graph. So this was pretty quick to be able to plug in, but a little tedious with all the F's. So there's actually an even quicker way we can do it on the calculator. So the 0.2 will go out front again, and then parentheses. And then we're going to have to type in on the keypad the command sum, then parentheses, then SEQ for sequence. And then there's 5 things that we're going to list. We're going to put the function that we were subbing into, so x squared plus 1. Then the independent variable, so x. The next thing we have to put in is the first interval's reference x value. So in that first rectangle, which x value did we sub in to get the height? Well, for us, that was 0.2. The next thing we'll put is the last rectangle. What x value did we sub in to get the height? And for us, that was 2. And then lastly is your step size when you go from one interval, or in other words, the width of in each interval. So it happened to be 0.2 for us here. So now I have 1, 2, 3 parentheses I have to close. So before we put that in the calculator, I just want to label what each of these things were. So this was our function. This is our independent variable, which should be x for us always. This is our first, I'm going to call it the reference x. This is the last reference x. And this, we're going to eventually call this our delta x, and that's going to represent the width of each interval. I'll add that here, width of each interval. So the last thing we want to know about this, because it is an approximation, it's not the exact area that's under the graph, we want to know, is this an overestimate or an underestimate? Well, in this case, it would be an overestimate. And we would say, since the rectangle area are more than the actual area. And you can start thinking about what feature of the graph is causing this to be an overestimate when we do right-hand endpoint references, but we're going to talk about that more towards the end of the video, but you can be starting to think about that. So we still haven't yet punched this in the calculator, so let's take a moment to punch this in the calculator and just confirm that it will give us 5.08. So we've got 0.2, we'll start a parenthesis, you're just going to type in sum, start a parenthesis, SEQ for sequence. Then we've got our function, so x squared plus 1, comma is down under the pi button next to the O, our independent variable, comma, 0.2, because that was our first interval's reference, x reference, 2 was the last interval, and then 0.2 for our step size. And if we hit enter, notice it gives us that same 5.08 back. So when you put this in the calculator, that's probably the way you want to do it. You don't want to have to do the F1s and everything. Now, our first exam in this unit is a no calculator test. So if I wanted to give you one like this, what I could do is I could just say, okay, tell me what would this command be that you would type in the calculator, and you would write down this whole 0.2 times some sequence thing, and then if you can do that, then I would know that you could type it in the calculator and get what the number is as well. Okay, so that's a right-hand endpoint Riemann sum. Let's go to the next slide, and now we're going to do, well, what if it was a left endpoint Riemann sum? So all we're going to do is determine the height of our rectangles by where the y value is on the left. And I'm going to start with the furthest to the right interval here, just because it's more drastic when I'm drawing it. So in this last strip here, the left edge hits the graph there. So that will be my rectangle that I'll use. And the next one, the left edge hits the graph there. So we'll use that height, and so on. So the height of each rectangle we're going to find the area of is determined by the y value of the left edge of the interval. So if we were to write this out the long way first, we'll write it out but not type it in the calculator. We would have 0.2 for our width. And then the heights, the first one will be at 0 now, because that's the left x value of the first interval, plus f of 0.2, because that's the left edge of the second interval, plus f of 0.4, and we'll keep going 4 ways. We'll have 0.6, 0.8, 1, 1.2, 1.4, 1.6, and then the last interval goes from 1.8 to 2. So the left edge of that would be 1.8, so our last one we're doing is 1.8. And note, if you count those up again, there is 10. So that matches our 10 strips that we had. But we've seen that there's an easier way to put this in the calculator. So the 0.2 parentheses will have our sum sequence. We'll have x squared plus 1, x. Our first x reference point now is 0, last is 1.8, and the step size is still 0.2. Now, because we just put this in the calculator before, we can just scroll up, highlight it. And the only ones we have to change are that first x reference point is 0, and then we've got 1.8 for the last one. Everything else is staying the same. And if we hit enter, we should get 4.28. Now our notation, sometimes you'll see for this is L10 for left-hand Riemann sum with 10 subintervals. And sometimes this is called left-hand endpoint method, or they might call it the lower sum because your reference x value is on the lower end of each interval. Now, when we added up the area of all these rectangles, notice there was some shaded space that was not included. So this would be an underestimate. And we'll say since sum of the actual area not included. Now, I want you to be thinking about what feature of this function is causing it to be an underestimate when we do left-hand endpoints, and we'll talk about that at the very end of the video. But what we know so far is 4.28 was an underestimate, 5.08 we figured was an overestimate, so we can conclude now that the actual area is something in between 4.28 and 5.08. Now, one other method we'll see is the midpoint method. So again, I'm going to start by drawing in the last strip. The midpoint method is you find the y value that's right at the middle of the interval, and that's going to dictate your height. So once I put that midpoint y value on the function, I go over straight to the left and right. So here's like my midpoint. I'll go over left and down, right and down. And notice one of the advantages of the midpoint method is we've got a little bit of overestimate and a little bit of an underestimate. So often, the midpoint method ends up being a better estimate than the left-hand or right-hand version. Now you might ask, well, then why do we even bother doing left and right? Well, a lot of times on the AP exam, Riemann sums we end up doing when we only know a table for a function and don't have the actual equation. And then based on the table, you might not have the midpoint values to work with. So we're going to jump right to doing this the quick way on the calculator. So we have 0.2 out front because our base of each rectangle is still 0.2. We're going to have some sequence. Oops, so it should be parentheses, not commas. We'll have our function x squared plus 1, our independent variable x. Well, now we got to think about in that first rectangle, what is our reference x value? The interval went from 0 to 0.2. This is the midpoint method, so we're using a reference x value that's at the middle of that interval, so we should have 0.1 for our first one. The final interval here went from 1.8 to 2, so the midpoint x value would be 1.9, and then lastly our step size was just 0.2. So again, we've only got to adjust those two that we had changed before, so you can scroll up and highlight the previous one, hit enter to bring it down, and we can just adjust those two things. We got the 0.1 for that third comma thing and 1.9 for the second last one, and we got 4.66 for that estimate. Now the shorthand notation you would sometimes see for this is m sub 10 to represent the midpoint method with 10 sub intervals. All right, so that is our three main methods to work with. Well, say we've got these rectangles, how could we make them more accurate? So we're going to show you a little demonstration. So we're going to just, for argument's sake, do it with left-hand rectangles. So there's one rectangle if we only did a single rectangle for the whole space we're trying to find. And I'm just going to let this run for a second, and notice we're adding or increasing the number of rectangles we're doing each time. So this now looks like it's at n counter over on the left. We're at 15 rectangles, 16, 17. Now notice as the number of rectangles increases, the base, that delta x of each interval, is getting smaller and smaller and smaller. As that delta x, the base, gets smaller and smaller and smaller, notice that orange space, which is our Riemann sum, which is approximating the area under the curve, is becoming a better and better estimate. So as that number of rectangles becomes larger and larger and larger, it becomes a better representation of our exact area. Well, what could we maybe do to make that even better than we have currently? Well, if you keep adding rectangles, it's going to get even better. So the idea of what we're going to do is we're going to let that number of rectangles n, we're going to let it approach infinity. So I can't remember if I put this in the notes packet or not. If not, it's in the colored calendar packet. But what this is saying here is if we let our number of rectangles approach infinity down here at the bottom, our intervals are going to get so small that it's not really going to matter if you use left hand, right hand, or midpoint as your reference point, because the intervals are going to be so super skinny, it's going to be inconsequential picking between those three. So that's just saying that there's really very little variation where that reference point is in the interval, and they would still all be rectangles that you're adding up. Okay, so we're going to see if we can do one example together, and then we'll finish off talking about the overestimate, underestimate stuff. So we've got a new function now. We've got the interval 1 to 4, and we want to do 50 partitions. So to find your width of each interval, which we call delta x, you do where your interval ends, so 4, minus where your interval starts, so in this case 1, divided by your number of partitions, so 50 in this case. So that's going to give us 3/50ths, which is the same as 6/100ths, which would be 0.06. We're going to use midpoints, so technically our notation would be M50 to represent midpoint reference point with 50 strips or partitions that we're doing. So we're going to have 0.06, then we'll have some sequence. We'll start with our function, which is 8 over x. We've got x. Now we've got to think about the midpoint of our first interval. Well, this first interval here starts at 1, and it should end 0.06 later, because it's got a width of 0.06. So we're going 1 to 1.06. So we've got to think about what's the midpoint of that, and right in the middle would be 1.03. Well, this last one goes till 4. And remember, the width is 0.06, so that then should be 3.94 is where it starts. So that's our last strip that we would have somewhere in here. The midpoint reference point of that would be 3.97. And then our last thing is how wide is each strip, that width, which is just 0.06. So we'll go over to our calculator. We'll maybe type this one in this time. So we have 0.06 times our sum sequence. We've got our function of 8 divided by x, our independent variable of x. We had our 1.03 that we started with, the 3.97, which was our last midpoint reference point, and we've got our step size of 0.06. And we got something that's not nice. AP rounding standards, 3 decimal places, so we got 11.089 for that. This process, again, is called doing Riemann sums, when you're adding up a bunch of rectangles, and it approximates the area that is under that graph. So the last thing for this video is what feature of the graph is really determining if it's an overestimate or underestimate. Well, in this first one, we want a right-hand Riemann sum. So I'm just going to randomly draw one of our rectangles. Here's the base. The height should be determined by the right edge. So we would stop there and we'd go over. So this one would be an underestimate. And let's look, this is concave down. Imagine it was concave up, but still decreasing. So something kind of like that. Notice if we did a right-hand endpoint, it's still an underestimate. So this is an underestimate since it's decreasing. Well, now this next one, notice, is an increasing function, and we want to do a right-hand Riemann sum. Notice now that's an overestimate. And even if it was concave up and increasing, it would still be an overestimate. So this one is going to be an overestimate since it is increasing. So I think if you are asked a question like this, it's helpful just draw in one of those rectangles, and it makes it pretty easy to see which one it is. That's it for this video. Any time left in the period, you can start working on your homework, or feel free to work on your next problem set as well. Have a great rest of your day.